Okay, in the last video, we have proved so-called independence of a path theorem. So basically, it says if you have two points, A and B, and you have rectifiable curve, two rectifiable curve, gamma 0 and gamma 1. And these two rectifiable curve are fixed endpoint homotopic, fixed endpoint homotopic. Then fixed endpoint just means you can deform gamma 0 to gamma 1 curve by curve, like continuously deform from gamma 0 to gamma 1, right? You can move gamma 0 continuously to gamma 1. That's a fixed endpoint, and these two endpoints are fixed. Then we know the analytic function integral along gamma 0 is equal to the gamma 1. This is a so-called independence of a path theorem. All right, and this is a corollary of a integral f along gamma equal to 0 if gamma is homotopic to 0. The Cauchy integral from the Cauchy theorem, Okay, and this property is very important. F is always analytic. This theorem is always important, and this region, we want to specifically mention the region, the domain of F with such property. So that's definition 6.14. Not for every region, not for every domain, the function has such property. Remember that the integral theorem, first we require the winding number of gamma with respect to W is always 0 for all W outside G. And clearly, if you have a donut shape, then that's not, and gamma, if gamma is like this, then the W inside the winding number is not 0. So this region, we say this region G is not good enough to guarantee the Cauchy theorem. Cauchy theorem says whatever closed rectifiable curve with such property, or whatever closed rectifiable curve homotopic to 0, then you can always have such integral equal to 0, vanishing. All right, so we want to give a name for certain region G, guarantee the property, the integral, the Cauchy theorem. Okay, so an open set G is so-called simply connected. Simply connected if G is connected and every closed curve in G is homotopic to 0. All right. So in the definition, simple connectedness has assumption it must be connected first, and then it claims every closed curve homotopic to 0. All right. Okay. So for example, for something like this, if we have two open disk disjoint, even though when you have whatever closed curve, for example, this is a closed curve, because closed curve is continuous, so its image must be contained in one of those disks. So even the second condition is satisfied for every closed curve is homotopy to 0. But because this the union, we're talking about the union of two disjoint disks. Even though the second condition is satisfied, but these two disjoint disks are not connected, so this set is not considered as a simply connected. This set is not considered as a simply connected. All right, we must require they are joined, they are connected first. Okay. Okay, because this is connected, we see that every closed curve here, we don't even require the rectifiable, because rectifiable is used to measure the length, but this is a topological concept. There's no length requirement. So with this simple connectedness, we have the Cauchy theorem, the fourth version. Cauchy theorem, the fourth version. Okay, it says if G is simply connected, then this integral f along gamma is always 0 for every closed rectifiable curve. Rectifiable curve. And every analytic function. Rectifiable curve gamma analytic function f. Okay, so because every closed rectifiable curve will be homotopic to 0, then by the second version. Okay, so we have 4 versions. Version 1, we use the winding number. Of course, we have sigma, gamma k with respect to w equal to 0. This is version 1. You check that. Version 2, we say the requirement homotopic to 0. Gamma is homotopic to 0. But we didn't prove it. We proved the version 3. Version 3 says if you have gamma 0 homotopic to gamma 1, they are both closed rectifiable and they are homotopic, then the integral are equal. This is version 3. And then you apply version 3 to version 2 to get the version 2. And then this is a version 4. The version 4, because version 4 already include that all the closed curves are homotopic to 0. So second version is satisfied. Simple connectedness. So second version will imply the version 4. So those are the relations. All right. And after version 3, we have a corollary. Here we have a corollary. It says if gamma is homotopic to 0, it implies the winding number is 0 for all w outside G. All right. So after version 3, we have the corollary. So you need to get a lot of different versions, see the relations between them and the difference between them. All right. Okay. So in the next paragraph of the textbook, the author gave a long comments about the simple connectedness. Simple connectedness. This word should be written like this. Simple connectedness. Okay? It gave a little discussion about the simple connectedness, and he also mentioned a characterization in the chapter 8. In chapter 8, the following theorem is proved. A region G is simply connected if and only if and only if the extended complex plane without G, its complement in the extended complex plane, is connected in the, of course, extended complex plane. Okay, so this is a simple connectedness in a complex plane. All right, simple connectedness is a very important topological concept. In the complex plane, we have such characterization. Of course, we will not be able to prove this theorem in this semester's analysis, complex analysis. Even in the next semester's complex analysis, we don't have enough time to discuss this theorem. But we just get the feeling about the simple connected. Remove this set, the complement is connected. And the author gave a concrete example. It says if this G is complex plane but without the origin, so it's like this. The origin is missing. Then you can see that if you have a unit circle, then unit circle will always have one in number 1 with respect to the origin. So this G is not simply connected. G is not simply connected. But we can see that C without G is a singleton. It is connected. While C infinity without G is a union of infinity and 0. This is not connected. So this example tells us in the characterization you have to consider the extended complex plane. You have to consider consider infinity. You cannot drop it. If you drop that infinity, this statement is not correct. All right? Okay. So that's the little discussion or the comments about the simple connectedness. We just try to get advanced theory to understand this concept. It has to be connected. All the curves closed curve should be able to shrink to a point. No holes, no holes. Basically, simple connected just means no holes. If you have a hole, you cannot shrink it. Shrink a closed curve around it. All right. So next, we're going to prove a very important corollary. It says if G is simply connected, and F from G to C is analytic, in G, then F has a primitive in G. F has a primitive in G. Remember that we actually proved a similar result in the last section. In the last section, we actually showed that if you have an open disk, this type of a theorem is correct, right? Let me see if I can find. Yes, actually, on page 73, the proposition 2.15. Proposition 2.15, you actually show that if you have f analytic in the open disk, then f will have a primitive. When it has a primitive, the integral of f along the curve will closed rectifiable curve will be 0. That's the first baby example of the Cauchy theorem. Okay, so it's a long time ago. And we also mentioned the Moreira theorem. Remember that the Moreira theorem, the triangular path integral 0, then f has to be analytic. Right? And then this moment we're going to show whenever you have a simply connected domain, then it is f always has a primitive. Then you can see the proposition 2.15 is just a special example of this. All right. Okay. So now let's prove. Oh. Well, this is a remark. It's not part of a statement. The statement stops at this point. Proof. Let's try to show f has a primitive. Okay. Now we first fix a point A in G. So we select A in G. And for any Z in G, assume that gamma 0, gamma 1 are two rectifiable curves. Connecting from A to Z. Okay, so you just have A is here, Z is here. You have a gamma 0, you have a gamma 1. Then you just randomly choose two rectifiable curve connecting from A to Z. Then what we know? We know that the gamma 0 minus gamma 1, like from gamma 0 is from A to Z, and negative gamma 1 is from Z to A. So is a closed rectifiable curve in G. Okay, we got a rectifiable curve in G. And we know G is simply connected, so gamma 0 minus gamma 1 is homotopic to 0. Gamma 0 and gamma 1 are homotopic to 0. If they are homotopic to 0, what we get? We know the integral f along gamma 0 minus gamma 1 is equal to 0. Right? This is a fourth version of a Cauchy theorem. The fourth version of Cauchy theorem. And this integral can be written as the integral f along gamma 0 minus the integral of f along gamma 1. Let me try to find another pen. Okay, so this implies, moment. This implies the integral of f along gamma 0 is equal to the integral of f along gamma 1. So it tells us the integral does not depend on the choice of the path, independence of a path theorem. Right? So we get, so for any z in G, we choose a rectifiable curve from A to Z and define capital F of Z to be the integral of f along gamma. Capital F of Z is well defined. So this process is just the proof of a well-definedness. Okay? So whatever. All right. Now we're going to show this capital F. Capital F prime of Z is little f. Capital F is a primitive. Capital F prime is the derivative, right? Fz minus Fz0 over Z minus Z0. So let's try to compute the derivative. So let Z0 be in G and R greater than 0 such that the ball centered at Z0 with radius R is total contained in G. Alright? And now let gamma be a curve from A to Z0. So we have A, whatever place, Z0 is here. This is a gamma. Right. And R is here. And inside this disk R, we choose a point Z. Let Z belong to the ball B0R. B0R. This R cannot be very large, but the R can be very small. Okay, R can be very, very small. So let Z be in the open disk B0R. Then you see here we directly connected the Z0 and the Z. Let gamma Z be gamma, like from A to Z0, plus from Z0 to Z. Here is a straight segment connecting Z0 and Z, because you are inside the open disk, so you can just use direct segment. Right? So what we get gamma 0 is a curve from A to Z, whatever. This original curve should be rectifiable. Your union segment is still rectifiable. All right. So we check this f capital Z minus f Z0 over Z minus Z0. Fz is integral along gamma Z f minus integral f along gamma over Z minus Z0. And gamma Z is the union of two pieces of a path. So it becomes an integral f along gamma plus integral f along z0z minus f along gamma over z minus z0. So it is 1 over z minus z0 integral f z0, right? And f z0, if you want, you can write this way. Here is a constant number. So you integrate constant number, you get the segment. And segment is the length of segment is a z minus z0, not the length, the vector of z minus z0. Cancel with this coefficient, you still get f of z0. So if you do subtraction, with opposite value, it will be less than or equal to z minus z0 integral f z minus f z0 dz, right? Okay, so this part will be similar to the proof of the Moreira theorem. F is continuous. Then for any epsilon, there exists R prime such that z minus z0 less than R prime, f z minus f z0 will be less than epsilon. So this is uniform. So this difference, opposite value of difference, will be less than epsilon integral of epsilon times its length. So it is epsilon times opposite value of z minus z0, and you cancel that, you will get epsilon. Here you directly get strictly less than, and this implies this derivative is equal to little f. All right, so this part you only use the continuity of f. You only use continuity of f. And why do we require f to be analytic? So there's no way to use analytic. Analyticity is used to guarantee that our f is well defined. Capital F is well defined. This part we use analyticity. In the Moreira theorem, they have the triangular path over the integral over triangular path is equal to 0. That condition is guaranteed is used to guarantee the definition of a derivative is the guarantee the primitive is well defined. So we have two different conditions. Those conditions are both used to make sure that capital F is well defined. Does not depend on selection of a path. All right, so that is the difference between them. So Moreira theorem and this theorem are very close, but they use two different conditions to guarantee the primitive is well defined. The primitive function is well defined. Okay, so Moreira theorem and this theorem. Oh, okay, here we finish it. And this theorem use two different conditions to ensure that capital F of Z is well defined. They're both defined by the integral. They're both defined by the integral from a fixed point to the other point along the rectifiable curve. And when you have such definition, you have to make sure that because you have infinitely many choices about the path, you have to make sure that the path, it is a path independent. All right, so that's the difference about the Moreira theorem and this theorem. After you finish that, you will see that this is almost trivial, the same identical statement. Here we only use f is continuous. And that's why in the Moreira theorem they only require the f to be continuous, because the well-definedness is guaranteed by another condition. All right, so one of a quite interesting corollary from this is this theorem or this corollary. From this corollary is the following. Let G be simply connected, and f from G to C be an analytic function such that f of z is never equal to 0 for any z in G. Then there is an analytic function G from G to C such that f of z is equal to the exponential of g of z. In other words, g of z is a logarithmic of f. Okay, we can always find one. So it just means it's not unique. Of course it's not unique. G plus z, check here, g of z plus 2 pi I also satisfied. So this can be another function. So G is not unique. If z0 in G and EW0 is equal to f of z0, if you have some fixed point requirement, some evaluation requirement, we may choose G, the function G, such that G of z0 is equal to W0. We can really design this function to satisfy the evaluation. Right? So it's like the definition of a logarithmic function. Remember, in the complex analysis, logarithmic function, we have the principal branch. We just remove origin and the negative x-axis. We cut it along this negative real axis, and the rest of the region will be simply connected. Right? So actually, if we let f of z is just as z, f of z is an identity function, then G is whatever simply connected region, but not including 0. So we could do something like this. So you remove the origin and you do whatever curve to infinity. This curve is not finite curve. It will approach infinity. When you do this such cut, it's like a cut. When you do such something like this, the rest piece is called G. Then by this corollary, assume we prove this corollary, we can also find an analytic function G from the same domain to C such that G exponential of G is equal to Z, or we can write like the G of Z is a log Z. But in this part, the formula will be weird, right? Because it's not straight. You have to be very careful. It just satisfies the property of a G, but not share the same formula. This formula is not that bad. Remember that it's a you have the logarithmic function of a modulus plus 2, not 2 pi, theta, I theta, I argument, and this argument is between negative pi and positive pi. So it's still very neat, but here it's not that neat. So we cannot just write it like log z, because you write log z, you have to clearly write down the condition, but that condition will be so crazily depending on this selection of g. So the best way to write is to say g composed with exponential function z. All right. So you can do whatever cut from the origin to infinity. It's like, remember that we have that discussion. This G equal to C without 0. This is not simply connected. It's not simply connected because infinity minus G contains infinity and 0. It is not connected. How can we make it connected? You just get a curve from the 0 to infinity. You join these 2 points. You join these 2 points, then C infinity minus G will be connected. Then G is simply connected. When G is simply connected, we can do such stuff. We just try to connect it origin to the infinity in whatever way. It doesn't matter. We just want to connect this, right? Okay, so that's a remark. That is just a remark. Now let's see the proof. Let's see the proof. Okay, so f is not equal to 0 for all z in G. Then f prime over f is analytic in G, right? It's not 0, so you can put it on the denominator. An analytic function over analytic function is still analytic, so it's analytic function. Analytic function, this is simply connect the regions, so by the previous corollary. By the previous corollary, f prime f has a primitive G in the region G. Okay, we have a primitive. This function is analytic, right? Okay, so define h of z be exponential of G1. Let's call it G1 of z. It's G1 of z. Okay. Primitive, a primitive. So you can add any constant, right? You can add whatever constant. So that's we never say the other stuff. We just pick up one. So you have a composition of a exponential function with exponential function, so h of z is analytic. H of z is analytic, and we know exponential function never be 0. Okay, and h of z is not equal to 0 for all z in G. Whenever it's not a 0, we can put it in the denominator. So f of h is analytic in G. It's analytic. Now let's check the derivative. Derivative, we have the quotient rule. F prime h minus f h prime. F prime h minus f h prime. Okay. So let's check. Let's check one more. F prime. You see, f prime over f is g1 prime. So f prime is f g1 prime. Okay? F g1 prime. H prime. H prime is exponential function has a derivative exponential function itself. And then you differentiate the internal function g1 prime. Exponential g1 is h, it's h g1 prime. Right? This is h and g1 prime. So this is h prime. So with this computation, let's see this derivative, f over g prime. F prime is f g1 prime times h minus f h prime is h g1 prime over h squared. Correct? So we just try to write down what prime f and h prime is. Okay, so you see the numerator is 0. The difference from the numerator is equal to 0. So the derivative analytic function is constant 0 in G. So what do we have? We have f over h is equal to c, a constant. Then what we have? We have h is c. F is h. C times h is c times exponential of g1 of z. And c, a complex number. C is not 0. Non-zero constant number can always have a exponential of c prime. So c is equal to exponential c prime. Well, you can pick up whatever, not whatever. You definitely have a lot of choices for c prime. g1 of z. So f of z is equal to exponential of g1 of z plus c prime. Correct? So we prove that g1 of z plus c prime is analytic, of course. So we prove the first part. And if fz0 is equal to exponential of w0 is equal to exponential of g1 of z plus c1 prime. So you see here, this quantity z0 is equal to this exponential of w0 is equal to exponential of g1 z0 plus c prime. So then there is an integer k such that g1 z0 plus c prime plus 2k pi I is equal to w0. 2k pi is equal to w0, right? And then you define, we can define g of z to be g1 of z plus c prime plus 2k pi I. Then we satisfy the condition. Correct? So by this way, we satisfy the evaluation condition. Okay, so you see here the simple connectedness has those one by one corollary. You see this corollary is about the existence of a 6.17. 6.17 is about the existence of a logarithmic function. Whenever you have a simply connected region and fz is not equal to 0, you can always define a logarithmic function. 6.16, you have primitive. Every analytic function will have primitive. 6.15, you have a Cauchy's theorem, the fourth version. So they all depend on, you see, simple connectedness. There's no other requirement. Simply connected, and simply connected. Not equal to 0 is a natural requirement. It's not additional strong condition because exponential function can never be 0. Logarithmic function cannot be defined at 0. So that's a natural condition. So in the textbook, the author also mentioned in chapter 8. Chapter 8 is about the simple connectedness in the complexness. Okay. In chapter 8, they prove that the 6.15, 6.16, 6.17 are all equivalent to the simple connectedness. But again, here we just mention it and try to emphasize the importance of simple connectedness, but we will not prove it. Okay? That's a remark. And next, because it's so important, let's give some symbol. If G is an open set and gamma is homologous to 0. Homologous to 0. In symbol we write like a gamma is 2-tiered equal to 0. If the winding number of gamma with respect to W is always equal to 0 for all Z in complex plane without G. This is a condition in the first version of Cauchy's theorem. In the first version's Cauchy's theorem. Okay? So first version Cauchy theorem, we use a winding number. Second, third, and the fourth version Cauchy theorem, we use the homotopic trivial or homotopic equivalence. All right. So homotopic to 0, we know it will imply the winding number equal to 0. But the winding number equal to 0 here, we call it homologous to 0. So 1-tiered will imply 2-tiered. Here, we just gave this winding number equal to 0. This condition, a name, is not a new concept. All right? So we finish this section. This section is about the Cauchy theorem, but in the homotopic version. Let me see the exercise. Well, on page 95, you can try exercise 1, 2, 3, 4, and 8. Exercise 8. exercise 8 give us a nice example. Is the graph is perfect, very good. Okay, of course, other exercises are also very good. If you don't have time, you can just do this. Okay, thank you very much. Thank you.